Well, let's see. The first thing I want to know is how much time the ball spends in the air. And that's governed entirely by its vertical motion. Remember this equation? Let's use that. Though maybe I should write delta y instead of delta x to emphasize this is vertical motion. Well, I know that delta y, the total distance the ball moves, is just h. And the ball starts at rest, so I can ignore this term. That just leaves me with this, 1/2 gt squared. Remember, instead of a, I wrote g, the acceleration due to gravity. That tells me the time the ball spends in the air is twice the height over g and the square root of that. And when you plug in 1.2 for h and 10 for g, you get a value of 0.49 seconds. Okay, so that's how long the ball spins in the air. Now let's analyze the horizontal component of motion. And that's governed entirely by the electric force. And remember, the electric force is equal to Q times E, which in this case would be 0.1 times 100, or 10 newtons. Well, that 10 newton force is causing an acceleration. And we know that F equals ma, so 10 newtons is equal to mass times the acceleration in the x direction, I should say, because we're just looking at that component of motion for now. Solving this, I find that this x acceleration is equal to 10 divided by the mass. And when I plug in 8 kilograms, I find that's equal to 1.25 meters per second squared. Well, now I can use my good friend. Delta x is equal to initial velocity times time, but there's no initial velocity, so I'll ignore that, plus 1/2 a, and that's this a, times the time squared. And the time we're going to use is that 0.49 seconds we found before. And that gives me a distance of 0.15 meters. So actually, if this was 1.2 meters, it only moved about to here. Good work.